Alright, so I got hung up the other night. Wasn't able to do my video as quick as I wanted to, so I apologize for that. I wanted to continue our conversation from the other night about anti-derivatives. These are going to be a huge part in what we're doing. Okay, again, Calc 1, all we did was find derivatives. We said, hey, listen, here's our function, f of x. And we said we need a graph that describes, how it's changing. Well, here it was a positive change. So, positive change. Here, it had zero change, because it was in a maximum. Oh, okay, cool. Here it had negative change, so negative. Oh, here it had zero, because it was at a minimum. Oh, weird. And then, up it goes. And not very fast up, because, it's not going very steep. And we talked about that. And the only difference between this function here and this function here, this guy here would be f of x, plus 2 or something, right? It's been jacked up. But they would have the same derivative, right? They would all have the same derivative. Didn't matter. That vertical shift makes no difference. And so this is f prime of x. So when we find the antiderivative, and we will refer to that as writing it like this, the antiderivative f of x. But Jay, I thought this sign was an integral sign. Well, that's true. It is. But when I write it this way, and I don't put anything on it, I just write it just like this, and you'll see what I mean in a minute. Okay, what this means is we're going to get some cap f of x, that is the antiderivative of it. And then we're always going to put plus c on the end because, hey, we don't know which of those plus c's are on the end. Plus 5, plus 2, plus 12, whatever it is. And that's how we'll always do it. Now, this is also referred to as not just the antiderivative. Sometimes it's referred to as the indefinite integral. Meaning that we didn't tell you on what region to integrate it between. What do you mean? Okay, well, again, this guy here is the rate at which this guy up here is changing. Okay, so if it were a velocity versus time function, like we did the other night, and I said, listen, this is this. Remember, this is equal to f prime of x. Okay, well, the antiderivative of v of, should be f of x, f of t. And I'll probably just call it x prime of t because let's talk about its displacement, right? So it's the change in displacement over time. So the antiderivative of this guy, which is the same as with respect to time, which we'll talk more about, is equal to, the antiderivative of this guy, x prime of t. So you're just saying it's cap x of t? That's right. That's all we're saying. Plus c. What would that mean? This is how far I go, okay, in a specified amount of time. What do you mean? Well, I'm saying that from A to B, how far did you go? Oh. So what we'll end up doing later on is we're going to put A and B here, here, and here, and here. And what we'll end up doing is, you're like, wait. So what you're saying is, Jay, you're finding the area under this curve. Yep. And you're saying that's a new graph. Let's call it x of t or whatever. And let's say x of t looks like this, or I don't know what it looks like. From here to here, that's what we're talking about. Right? Oh, okay, I guess. Well, what does that mean? Well, what we're going to end up doing, when I say this, how far I go in a certain interval, well, what are we going to do with those values? You need to know like a time frame from time equals 2 to time equals 5, between hours 1 and hours 3, whatever it is you're doing. Okay. When we do this, what you're going to end up seeing then is going to be x of t. We're going to write it like this. That's cap x, and we're going to integrate. We're going to evaluate it from A to B, and we're going to say it's cap x of b minus cap x of a. Okay. Now, why are we doing that? Okay. Now, both of these will have a plus c on the end. Initially, okay? Initially, we'll have that plus c on the end. Now, if you do that, you're going to get x of b plus c minus x of a minus c. And so when we get into doing actual integrals later on, soon, actually next week, well, this coming week, this is what you'll end up with. So what we're going to say is the integral from a to b of, and I'm going to write it with F's because that way people don't freak out. This is in general. That was a specified one for velocity. But generally speaking, we write it like this. It's cap F of B minus cap F of A. Okay. This has a name, and we're going to talk about that. That's kind of the whole point of starting this video out with that. Okay. If we don't specify a time interval, we simply write it like this. Or I shouldn't say a time interval. By the way, I use t here right now. I could have used x. It's whatever the independent variable is. Always forget your dt. We're gonna talk more about that this week. Okay, I'm gonna leave it alone for right now. You can look at it as like a useless appendage right now. It's not, but you can look at it kind of like that way for a second, like your appendix. Yeah. I haven't had mine since 1983 or so thereabouts. I haven't missed it that I'm aware of. So yeah, probably get along without it. This guy here is simply going to be f of t plus some constant. This is what we refer to as the indefinite integral. Wait, this one on top is different. Jay, what do you call that one? Wait for it, definite integral. This function would tell you how far we go between a certain place. That's fine. This one, technically, I should say it this way. This one here technically tells me, if you will, I'm going to keep it in terms of velocity and time, okay? We can mean other things too. Tells me how far I've come from t equals 0. Okay, this is assuming that I know C. This is assuming that I know C. Right? Now, if you look at this one up here, you're like, wait a minute here. What does this tell me? This tells me how far I've come between time equal A and time equal B. Okay? But what about the plus C? Well, this is a big concept, and I want to show this to you. When I was a kid, this never made sense to me. It wasn't until I taught physics for, I don't know, maybe a year or two, and then it finally was like, I mean, I got it, but like I never really like, whoa. I mean, whoa. So if you do this problem here, let's just go back to our conventional x and y. It doesn't matter to us. Okay. I want to know the area under this curve, and let's call this f of x, f prime of x rather. And I want to do it from a to b. So anybody knows, we simply take a to b, nice, of f prime of x dx, and we all know the answer is going to be cap f of x plus c. All right, now hold that thought just a minute. What would, and we need to evaluate this from a to b. We say that evaluate it from a to b. What that means is we're going to stick b into here. So you're going to f of b plus c. Now this is how far, if you will, it is from 0 to b. That is from here, the area all the way out to here. What we're going to do is we want the area between A and B. So what do? Well, you're going to minus, of course, f of A plus c. Now, of course, this is how far it is from 0 to A. And when we subtract them, look what always happens. Well, first of all, distribute your negatives, and it's f of b plus c minus f of a minus c. Just becomes this thing right here. And this is what the indefinite integral will always tell us. Always. I'm sorry, the definite integral always tells us. And now, if you come over here, you're like, oh, well, that's interesting. So, a couple things. So, first of all, like, okay, that's kind of cool. What if I wanted to integrate between, I don't know, this is f prime of x. This is A, this is B, and this is C. it seems pretty obvious to me, I think, I mean, I don't know, I feel like it's pretty obvious to me that the integral of f prime of x dx from a to b plus the integral I hope that's obvious to you. This area plus this area is the whole area. That is an actual rule that we will use later on. In statistics, if you've had a statistics class, you've seen that in class, and you've used that without even knowing it. You've seen this bell curve, the normal distribution, as we call it. Maybe you've seen this. I hope you've seen it. Maybe you've seen it somewhere. I look at this thing and I say to myself, all right, cool. Let's say that there's some, like I'm 6'3", so that puts me at about, I don't know, 2 standard deviations above the mean. Okay? In other words, you could talk about me being how tall are you relative to the rest of the population, the males in the U.S. Okay, well, it turns out that there's about 95-ish% are shorter than I am. Okay, well, what percent are taller than me? The rest of them. But this normal distribution, this curve here, is just an f prime of x. And what we do is we integrate technically from negative infinity up to some value of this f prime of x dx. And so when you took statistics, some of you were taught it correctly and said, hey, go into Excel and use a function. What that function did was it numerically integrated this region. It did that because this thing here does not have, this specific one, the normal distribution, does not have an antiderivative. It doesn't have one. So if it doesn't have one, what do you do? Well, you have to use numerical integration. But here's the best part. We know that the antiderivative from negative infinity up to positive infinity of this whole thing up here, which again, I'm not going to write out just right now, we know the entire region is 1. Because there's a 100% probability you will find a person's height, yes? Or in other words, 100% of dudes fall into this curve. Yay! They may be freakishly tall, they might be freakishly short, or they might just be somewhere blah in the middle. Well, we don't know, but they're on there. So then the question is, how much is out here? And some of you, of course, were saying the whole time, Jay, you're in the top 5%. Yeah, I know, I got you. Plus this, wait for it, a to infinity has to be 1. And then in statistics, what we always do with this is there's a function built into Excel. Oh, damn it. There's a function that's built into Excel. Oh, there we go. But not only is it built into it, oh, shoot. If you were taught the wrong way, as if it was 1987 again, you would look up a table in the back of the book, and it would tell you an answer. But it was always the area less than. What if I want this up here, Jay? Well, I minus it. Bloop, over to here. And you have what's left. But what is that? That is this rule from integrals that we have. Because it's the exact same thing. Okay? That's it. Now, 2 things that I want to focus on about this is this thing is called, and I'm going to let you in on a secret right now. This guy right here is what is referred to as the fundamental theorem of calculus. Part 1. Now, I don't remember which one's part 1 and which one's part 2, to be fair with you. Okay? What I want to do tonight, what did I want to do at the start of this video is only talk about this part of it. Jay, our book calls it part 2. Doesn't matter. There's 2 sides to this. This is the fundamental theorem of calculus. The fundamental theorem of calculus. What this, that's a U, by the way. What this theorem does, in addition to allowing us to find areas under a curve and things along those lines, is this is the theorem that takes what we do in 251, that is with integrals, and what Archimedes started doing zillions of years BC, and it marries the 2 together and says, hey, listen, one undoes the other one. What are you saying? I'm saying that this integral right here undoes the derivative. Whoa. Whoa. Hey, what does part 2 do? What does the other part do? It shows that the derivative undoes the integral. Whoa. I know. So that is a big deal. Now, how are we going to use this? Well, I'm going to show you how we're going to use it. Okay, but sit tight. We got this. That's the big deal. Now, some antiderivatives we mentioned. Okay, so we also said if you had just a good old-fashioned polynomial there. The antiderivative of a polynomial, as you know, is, well, let's see, what is it? It's going to be 1 over n plus 1 x to the n plus 1 plus c. Right? You mean x squared? Well, I'm going to add 1 to the exponent and then divide by it. It is the opposite of the power rule. Piece of cake. Piece of cake. Right? Integral of sine. From whence did sine come? This is where you'll probably end up screwing it up, because most people do the first time or two they do it, and don't panic. It comes from negative cosine. But I thought the derivative of sine was positive cosine. It is. It is. No, it totally is. The way I like to think of it is this: sine goes to cosine when you're doing derivatives. Nice. So when I'm doing derivatives, I go this way, right? But when I am going, when I'm doing integrals, I kind of go at it a little differently, right? I need to come at it from, well, let me see here. So what is the antiderivative of, what's the antiderivative of cosine, for instance? The antiderivative of cosine is sine. Well, it's just plus c, of course. Plus c. I just went from here to here, obviously. Okay. What about from minus sine? Well, the antiderivative of minus sine is cosine. But I didn't have minus sine, Jay. I had positive sine. I know. So what does that do? It just flips the sign. Just flips the sign. What a person can always do, hey, when you're done, am I right? I don't know. Take the derivative of this. 3 times this is what? 1 x squared. Yay. What's the derivative of this constant? Oh, boy. It goes away. Yay, I did it right. That's why we love these things. Most of these things are, it's a quick, easy check. Is it the right antiderivative? I don't know. Take the derivative. If it works, yay. If it doesn't, well, I mean, that's, you're wrong. So go fix it. What other ones do we do? Oh, the derivative of the natural log. Okay. Well, the derivative of natural log, if we do d dx, right, is 1 over x, right? Well, in other words, the antiderivative of 1 over x is what? Well, it's natural log. Well, kind of. Kind of. This one has a domain restriction, yes? This is x bigger than 0, which means this also would have a domain restriction. Because ln looks like this, 1 over x looks like this. That's true, but what? They have domain restrictions. Okay, we're only on the positive side. If you start with this fella here, this is not domain restricted, which means that 1 over x looks like this and like this. Ooh, well, not like that, stupid. That only zeros, you idiot. Nice. And so you're like, oh, it's got to be ln. Well, not so fast, Haas. Not so fast. In fact, it's the ln of the natural log of x. Well, obviously, this one doesn't change. It's the ln of the natural. It's the ln of the absolute value of x. Listen to me. What an idiot. Let's go look at the old Desmos.com. Come on, baby. Come on, baby. 1 divided by x. ln of x, you see, it's just that. Well, that's not acceptable. We got to have the absolute values in here. Come on, baby. Come on. Nice. Nice. And it just gives that mirror image across there. You'll see several you'll see several antiderivatives that are similar to that where, hey, wait, I thought that was different. Yep, it is. Obviously, d dx of e to the x is e to the x, obviously. The antiderivative of e to the x is what? It's e to the x plus c. Okay, that's the easy one. If you can't do that one, boy, we got problems. Later on, we'll get into, well, what if it was e to the 2x, Jay? Well, hold on. Let's do that. That's what is the derivative of e to the 2x? And you're going to be like, well, it's 2 e to the 2x. It's kind of like a power rule almost, right? Because you used the chain rule because it was a function in a function. Well, guess what? If you were going to take a wild stab at this, I mean, just think about this for a jiffy. What do you suppose the antiderivative of this guy would be? And you're like, it's like a power rule almost, Jay. It is. It is. I bet it's 1/2 e to the 2x. I bet you're right. And we're going to have a way to do that so we don't have to sit around and kind of like guess at it. We're going to have a technique for that. It's not going to shock you at all. Wait, it's like similar to when we did d dx of cosine of 3x. Well, the derivative would be minus 3 sine 3x, right? Because it's the chain rule. Well, what do you suppose the antiderivative of sine of 3x is going to be? That's a 3, by the way. Well, I don't know, but if I was a betting man, first of all, this should be negative. It's not a negative. You see that? It's not a negative, so it's going to be negative cosine. It was 3x to start with. I bet it's going to be 3x now, because if it's not 3x, it changes the shape of the graph, which is ludicrous. But what's going to happen? Well, there should be a 3 here, Jay. Well, there's not a 3 there, so it's going to be 1/3. And if you're uncertain, take the derivative of this. Well, that's negative 1/3. Well, actually, it's not true. What's the derivative of negative cosine? It's going to be positive sine. So 1/3 sine 3x times the derivative of the inside, which is 3. Hey, it worked. Yay. Again, some of these you're going to be like, oh yeah, that makes sense. How do I do that, though? Is there an algorithm or a pattern? Yeah, of course. So that's what we're going to spend our time on, right? Some of them are fairly straightforward. Some of them are going to be just butt ugly. This one is one that you're like, hey, what's this one? You don't want to know. We'll wait for later. What about this one here? This one seems, I bet this one's easy. It's not. You're going to want to wait till later. Okay. So some of these are going to be uglier than others. And you're like, well, I don't even... I don't remember that being a derivative of anybody. Though, if I was a betting man, I would imagine, I'm just saying, I'm going to go on a limb here. I bet there's going to be some signs over here on this side. And I bet there's also going to be some x's, maybe an x squared or something floating around over here. But I have no idea what it is. I mean, you shouldn't, because it's not one that we've memorized. The antiderivatives I want you to feel comfortable with are the common derivatives that we did in Math 251. Nice. Now, the last thing I want to suggest about this is this. If I have a nice, easy function, and we're going to do a nice, easy one today. You're welcome. This is f prime of x, and it's 2x plus 2. And what I would like to do is I would like to find the definite integral, rather. Well, first the indefinite integral. So first of all, the indefinite integral would just be 2x plus 2 dx. What we can do is we can attack this in pieces because it's additive. I can actually break this into 2 parts. And I can do them separately. What is the antiderivative of that? What's x squared? It's 2x squared over 2, or just x squared, right? And then this one, this is 2x to the 1 divided by 1, which you look stupid doing that, so let's don't do that. It's just 2x. That's it. That is plus c. That would be your indefinite integral, right? Or if you prefer, the antiderivative. Nice. Nice. Now, what would you need to know in this problem? Well, you would need to know c. C is equivalent to, hey, what is the y-intercept on our new function? So if you recall, there's your 2x plus 2. Here's your x squared plus 2x. This function, that function right there, the purple one, describes the area under the green one. Okay? Now you think about that for a minute. But Jay, why is it 0 at 0? How much area have you got when you start at 0? How much area have you gotten? None. That's right. That's right. In fact, that's always going to be true, by the way. In fact, whenever you try to do this, this is going to be a big deal. I'm going to only hint it to you because I like you. You're nice people. If I integrated any function from a to a, the answer is always 0. That's because you're saying, hey, listen, yeah, stops the clock before it even started. I went from no time to no time. How far did you go? How far did you go between 3 a.m. and 3 a.m.? You mean 3 a.m. today and 3 a.m. tomorrow? I mean, no, 3 a.m. today and 3 a.m. today. There's no time, bro. We didn't move. Yeah, see that? And so as we do these things, kind of keep that in the back of your head too. We will come about with that. Now, if I wanted to know how much area there is between, so x equal 1 right here, look at that. At 1, I've gone 3. What does that mean? That means when x equals 1, I have traveled 3 from 0. Well, doesn't that mean plus c on the end, Jay? Isn't there supposed to be a plus c here? Now, hold on, I got you. Oh, this shouldn't be xx. What is that doing? Anyway, there it is. And you're like, well, look, Jay, if x is 1, look at this. What does that do? It's at 4. If x is bigger, oh, it's 5, it's 6, it's 12. You with me? Whatever, okay? Now, that just says, listen, I've gone 6.3. I am 6.3 units from 0. Okay? Now, if we put this back to 1, or wherever we were to start with, I think it was 1. There you go. It says we've traveled. As I say, we've traveled 4 units. We are 4 units from the start line. Okay? 4 units from the start line. If c is 1. At x equals 2. Oh, damn it. I don't even know how I get that. At x equals 2, we are 9 units from the start line. 4 units down here. How far have we traveled between 1 and 2? We've traveled 5 units. Now watch this. Let's make this bigger. Okay, whatever. Who cares? Here we are here. We are at 6.8. And we are at 11.8. The difference between those is what? Well, it's 5 again. It will always be 5. Because it doesn't matter where you start. If you're traveling at the same rate, that is, you have the same derivative, but then between the next 2 points, A and B, you will have always traveled the same distance between A and B. Doesn't matter where that A happens to start at. Doesn't matter. Okay? And that is what we are going to say. This is, again, the antiderivative, or the indefinite integral. If I rewrite that as the integral from 1 to 2 of 2x plus 2 dx, then of course we know that this is the antiderivative, x squared plus 2x, but we're going to evaluate it from 1 to 2. That's what the kids say. And no plus c, because again, that's that idea. When I subtract, what happens to that c anyway? It goes away. So this ends up being 2 squared plus 2 times 2, which of course is whatever it is, minus 1 squared plus 2 times 1. And so, of course, that's 4 plus 4 is 8, minus, this is 3. is 5. Yay! That will always be that difference. Okay? So again, this is the fundamental theorem of calculus. That is the part that I want to talk about in terms of that. Now, just one moment, please.